cover the topics of module 1, that is differential equations. And the topics which will be covered in this video are formation of differential equation, ordinary linear differential equation of second order, and ordinary linear differential equations with constant coefficients. Alright? Yeah, so very first we should know, before we learn how to solve a differential equation, we should know how to form a differential equation. So here we are going to start to learn how to form a differential equation. So with the help of this example, let us try to understand actually how we form a differential equation. Okay, so I am reading out the example. Find the differential equation of all circles passing through the origin and having centers on the axis of x, right? So we know that if a circle is passing through origin, it's passing through origin and having center on x-axis somewhere here. So let's say point of this center, that is C, are h, 0. Okay. Alright. So h is very small distance we can take from origin towards x-axis. Right. So that becomes radius as well. Alright. So we can write the equation, general equation of circle in this way by taking h, 0 as the center, and of course h becomes the radius. So here we can write the equation of circle passing through origin having center at h, 0 is x minus h whole square plus y square is equal to h square. On simplifying which we are getting this general equation, right? Of course h is an arbitrary constant which is very small. Yeah, if we differentiate it with respect to x, keeping y as dependent variable, right? So I am going to differentiate this equation. So that gives me as 2x plus 2y dy by dx minus 2h. X differentiation gives us 1 is equal to 0. So from here we can find out the value of this h, which was taken as arbitrary constant initially, right? So how we are going to form a differential equation? Actually, whatever we have assumed here from our side to form a differential equation, that is to be eliminated. So what we are doing, we are going to substitute this h from here, which we have differentiated, where in the given equations which we have here. Yeah, so here we will substitute it. So that's why we have substituted here x square plus y square minus twice x, and this is our h. So h is eliminated now, which was assumed, right? Alright, so on simplifying, we are getting this result, right? So in this way, we have formed a differential equation by eliminating arbitrary constant. Yeah, by eliminating arbitrary constant. Alright. Yeah. So in this way we have formed the differential equation of all the circles passing through the origins. We call it family of circles. Alright. Okay. So let's understand some more examples where we have to form the equation of the differential equations, right? So here we learn with the help of some more examples how we can form the differential equations. right? So suppose we are given some examples at as y is equal to f of x minus I t. Yeah, I'll erase it. I'll take this. So here, if I'm having a function like this, f of x minus iota into t, where x and t are the independent variables on which y is depending, and psi of x plus iota t. Right. So these phi and psi are what? These are arbitrary functions, by eliminating which we can also establish the differential equation. How come? Let's understand. So if I differentiate this y with respect to x, right? So what I'll write? I will write this as del y over del x. Okay. This y is depending upon x and t, so I can write here del y over del x, right? So it will be differentiated with respect to x. So I am getting here f dash x minus I t plus psi dash x plus iota t. Alright. Yeah. What is my purpose? My aim is to eliminate these arbitrary functions and I want to form a differential equation, right? Okay, so one more times, if I differentiate y with respect to x, so partially differentiating, I am getting this f double dash x minus iota t plus psi double dash x plus iota t, right? Give this as equation number 1. Now differentiating this y partially with respect to t, I am getting del y over del t as f dash x minus iota t into minus iota plus psi dash x plus iota t plus iota. Further, on differentiating partially with respect to t, del 2y over del t2, I am getting f double dash x minus iota t into minus iota once again. So this is minus iota into minus iota. Alright, once again I'll differentiate psi dash. So here I am getting psi double dash x minus x plus iota t into iota square. Alright, which on further simplifying I can write as del 2y over del t2 is equal to minus iota into minus iota gives me plus iota square, that is minus of f dash x minus iota f double dash iota t. Alright, yeah, here plus psi dash iota square means minus. Okay, so what I am getting? Minus 1. So here what I was getting? Minus iota into minus iota plus iota square, that was minus 1. Here iota square is also giving me minus 1. So that's why I am getting psi double dash x minus iota t. Give this as equation number 2. Right. So on adding 1 and 2, what I'm getting? If I add these two differential equations, these two partial derivatives, which is partial derivative of order 2, so what I'm getting, del 2y over del x2 plus del 2y over del t2 is equal to 0, right? Which is a form of Laplace equation, right? So in this way we have formed a differential equation of second order. Rather, I would say that it's a partial differential equation of second order. Okay, so in this way we can form the differential equation by eliminating arbitrary functions as well, and also by eliminating arbitrary constants, which I have already told you in my previous video, that how we can eliminate arbitrary constants to form a differential equation, right? So I hope it will be clear. So moving on to next. Let's understand what is ordinary linear differential equation of second order. Yeah, it's nothing but a general form. If I take here like a naught x raised to the power n dn y over, let me correct it. Yeah, dn y over dxn plus a naught dn minus 1 y over dxn minus 1 plus a1 dn minus 2 y over dxn minus 2 plus and so on a n y is equal to q, which is function of x only. So this is general form of ordinary linear differential equation with arbitrary constants as a naught, with constant coefficients as a naught, a1, a2, a3, an. If I am having this n as 2 at the max, so what I'm going to have? I'm going to have a standard form of ordinary linear differential equation of second order as d2y over dx2 plus px, which is function of x, y dash means dy by dx plus qy into y qx into y is equal to rx, where p, q, r are the functions of x only, and here the maximum order differential coefficient is d2y over dx2. So it is one example of second order linear differential equation, right? So here I have mentioned two types of differential equations, right? So this example is an example of second order linear differential equation with variable coefficients, and similarly I can write d2y over dx2 plus something a naught dy over dx, that y dash, plus a1 y is equal to some function of x. Alright, so this is the general example of second order linear differential equation with constant coefficients, where the coefficient of double derivative is 1 and rest are a naught, a1, which are constant coefficients. Understood? Yeah. So this is the difference between the two. Alright. Yeah, here I am going to tell you having the general form of linear differential equation of second order, which as I mentioned in my previous slide, that if P and Q, in place of P and Q, I am taking the constant coefficients, then that differential equation of second order is known as second order ordinary linear differential equation of second order with constant coefficients, right? And if all two P and Q are the functions of x only, then that is known as linear differential equation with constant of second order with variable coefficients, where right hand side part in both of the types of differential equations would be a function of x only, or 0, or some constant value. Right. So the solution of such differential equations would depend upon the nature of the right hand side. What is the nature of right hand side part of the differential equation? If it is 0, then only left hand side solution will be the complete solution or general solution. If it is a constant, then accordingly we'll solve. If it is a function of x, then of course in the case of when right hand side part is function of x and having a constant value, then in both the cases we are going to have some additional result in the complete solution, right? So we need to add that result in our journal solution or complete solution. All right. Yeah. Okay, now let's learn how we can solve linear differential equation of second order with constant coefficients. Suppose we have the standard form. Here, of course, d by dx is the differential operator, and which is denoted by capital D, and double, which is denoted by d square. Yeah, we are going to use these operators while solving such differential equations. Yeah, in short, we can write the differential equation like this: d square y plus px dy plus qxy is equal to rx, where p, q, r may be some constant, maybe some function of x only. Right? P and Q would never be 0 if these are 0. So that's become a very simple differential equation which can be easily solved by integrating. Alright. Yeah. So here we have to learn by taking P and Q as non-zero, some constant or the function of x. Alright. As I have told you in my previous slide, that if we have the journal differential equation as yn, means nth derivative of y, plus a naught yn minus 1 plus a1, it's a naught a1 yn minus 2 yeah, plus a2 yn minus 3 plus and so on a n y is equal to some function of x. So all these derivatives can be represented in terms of d, means differential operator. So I can write this as d n y plus a naught d n minus 1 y plus a1 dn minus 2y plus and so on an y is equal to qx. Right. So since we know that these all capital D are differential operators of various orders. But the nth term which is not having any differential operator, that means y is not differentiated then. So I can write these differential operators in a bracket and I can make this n minus 1 plus a1 n minus 2 plus and so on a n y is equal to q x. Yeah, so this bracket, if I write as polynomial in D, then in short we can write this as if dy is equal to qx. So this is standard form of ordinary linear differential equations with constant coefficients. Alright, so we have to learn to solve. Why I have written like this? Because this is going to be very helpful for us in learning this solution. How we are going to find out the solution of these differential equations. Okay. Yeah. Right. So I was telling that whenever we are solving the differential equation, that means we need to have its general solution or complete solution. That contains two parts. One is the complementary function, that is solution of the part. I will go to the previous slide. Yeah. Complementary function is the solution of left hand side part and particular integral is the solution of left hand side part. Okay, let's understand how we are going to find out the CF and PI. Yeah, so general differential equation I was having is if dy is equal to qx. So complementary function, to find the complementary function, we always assume as if dy is equal to 0. Alright, always remember this point. Whenever we are going to find out the complementary function, we need to assume that if dy is equal to 0. And keeping this in the mind, we find the solution of y. That is known as CF. Okay, now coming to PI. While finding out PI, we take the complete differential equation as f dy is equal to qx and our particular integral is nothing but 1 by f d. This is nothing but 1 by f d is what? A polynomial in operator, differential operator d, and qx is mentioned here. So now this we have to learn one by one how we are going to find out complementary function as well as particular integral, right? And after learning these two, we'll add the two solutions that will give us the general solution. I hope it will be clear. Yeah, here we have to first learn method of complementary function. How we are going to find out the complementary function by keeping f dy is equal to 0. As I have told you that we'll take f dy is equal to 0 for finding out our CF. Okay, so what we do initially, actually we need to find out the auxiliary equation with the help of this. How this is possible, one by one I'll explain it to you. For example, I'm having the differential equation which I had shown you here. Yeah, this one. dn plus a naught dn minus 1 plus this. Alright, so I'm going to use this differential equation. Yeah, here. That was dn plus a naught dn minus 1 plus a1 dn minus 2 plus and so on. An y was out, and here we have to take this as 0. Why I have written here 0? Because we are going to find out CF. So for that we take always right hand side as 0. Right, so these are differential operators. So when this is operated on y, then I am having what? Nth derivative plus a naught n minus 1th derivative plus a1 n minus 2th derivative plus and so on. An no derivative, that is equal to 0. Now this step is to find out the auxiliary equation is that we replace y by y dash by m, y double dash by m square, y triple dash by m cube. Similarly, I would say nth derivative of y would be replaced by m raised to the power n. Got it? So in this way, these replacements will provide us an auxiliary equation in small m, right? Which is mentioned here. An auxiliary equation in terms of small m. Alright. Then our next step is to find out the roots of this auxiliary equation, which is in terms of m. Okay. Yeah. So by anyhow, if we are getting quadratic, if we are getting cubic, if we are having biquadratic, by anyways we have to factorize the auxiliary equation which is in m, in terms of m. And by looking at the auxiliary equation, we can directly have an idea that how many roots we are going to have. It is, if it is of order 2, then 2 roots we are going to have. If it's cubic, then 3 roots we are going to have. Biquadratic, 4 roots, and so on. Nth order polynomial or nth order auxiliary equation is going to give us the n roots. Alright, so yeah, alright, so n roots, these n roots will provide us the complementary function, and all the cases of complementary functions will be depending upon the nature of these roots of auxiliary equation. Alright. So here we need to find out the roots of auxiliary equation. Alright, so I hope it will be clear. So I'm going to remove all the ink. Yeah. So first case to find out CF is when the roots of auxiliary equation are real and distinct. Then how we are going to have the complementary function. Okay. Yeah, so suppose we have the roots of auxiliary equation as m1 and m2, right? Then directly we can write the complementary function for f dy is equal to 0, and this complementary function is the half solution for a journal differential equation, which is ordinary linear differential equation with constant coefficients. So that CF becomes C1, when I am going to write this, when the roots of auxiliary equation are real and distinct. C1 e raised to the power m1x plus C2 e raised to the power m2x. Okay. Right, if we have more than 2 roots, then similarly we can write for the remaining roots as well. When? Always remember the condition when the roots of auxiliary equation are real and distinct. Then and only then we can use this formula to find out or to write the complementary function for the given differential equation. Alright, so I'm going to close this here. In the next video, we'll continue with this. Till then, keep revising.